In the previous video, we've seen an example where the demand at each store is uncertain. However, although the demand is not certain, you know for sure how much milk you still have when you arrive at the next store. Here in this video, we're going to look at the example of the inventory problem, where because the demand is uncertain, then the amount of inventory that you have at the beginning of next month is also uncertain. When we talk about deterministic dynamic programming, we have an example of an inventory problem. This one is very similar to that. The difference is that in that problem, the demand for each month is known for sure. Here, however, the demand for each period is not certain. It may be either 1 unit or 2 units, with the probability is the same between 1 or 2 units, because it says it is equally likely to be 1 or 2 units. And then everything else is pretty much the same. There's a production cost, and this is the production cost if you produce anything greater than 0. So if you produce 0, then the cost is also 0. And then you also have the holding cost, $1 per unit that is that you keep at the end of the period. And the capacity of the warehouse is 3 units. All demand must be met on time. And finally, at the end of period 3, if you still have some items left in your warehouse, they can be sold at $2 per unit. At the beginning of period 1, there is 1 unit of inventory in your warehouse. And then we would like to maximize the expected net cost during the next 3 periods. So there will be a pause on this video to give you the time to read this problem carefully before you continue. Now let's start at the very last month of this problem, which is month 3. At the beginning of month 3, we have I units of items in our inventory. Because we would like to minimize the cost, let's just write down all the costs that happened at month 3. First, we have the production cost, Cx. For x greater than 0, the function is 3 plus 2x. Now that is the production cost. Let's move on to holding cost. If the demand equals 1, our ending inventory is I plus x minus 1, because I is what we have at the beginning of this month, plus x is what we produce at this month, minus 1 is the demand. So the ending inventory is I plus x minus 1. The holding cost is $1 for each unit we keep at the end of the month. So this is actually $1 times I plus x minus 1. You just don't see the number 1 there, but it is actually there, okay? And you don't need to write it because 1 times something is just something. And then if the demand is 2, our ending inventory becomes I plus x minus 2. Again, I is what we have at the beginning, x is what we produce at this month, minus 2 is the demand. The holding cost is $1 for each unit that we keep at the end of the month. So again, this is 1 times I plus x minus 2. You may write down the $1 if you would like to be clear, that's also okay. Now, as usual, if the case is probabilistic and we say if this event happens, if that event happens, we must multiply it with the probability of the corresponding event happening. It means that we need to multiply that with probability of the demand equals 1, which is 1/2. And then for this second part, we also need to multiply it with the probability that the demand is 2. Because this is how we say this is the probability of that event happens. Okay? Similarly, for the salvage value that we obtain from selling our ending inventory, so if the demand is 1, the ending inventory again is I plus X minus 1, and we can sell them at $2 each. Notice that the sign is negative because when we sell our ending inventory, we obtain money. Okay, so the sign is negative. If it is the cost, the sign is positive because we would like to minimize the cost. So anything related to cost has the positive sign. Anything related to revenue has the negative sign. So this is for the demand equals 1. If the demand equals 2, our ending inventory is I plus X minus 2, and we can sell them all at the price of $2 each. So you see here 2 times I plus X minus 2. Same as before, we need to multiply each of this thing with the event that that thing happens. So we multiply the first one with the probability that the demand is actually 1, and that probability is half. We multiply the second term here with the probability that the demand is 2 units, and that probability is a half. Okay, so this is the recursion for stage 3. You see that the key is first you calculate the expected cost or revenue if the demand is 1 and if the demand is 2. However, do not forget to multiply each of those values with the probability of the event happenings. Probability of the demand equals 1 and probability of the demand equals 2. So that's really the key for formulating the probabilistic events. So that was the formula for stage 3 recursion. Now here's the computation if we are given the numbers. If you recall from the problem, our warehouse can only contain at most 3 units of inventory. That's why the possibilities for I, our beginning inventory, is from 3, 2, 1, and 0. So we may have at most 3 units of inventory, and up to the possibility that we have nothing in our inventory. If we have 3 units as the beginning inventory, the possible decisions is either 0 or 1. We may produce 0 because you know the demand is at most 2. So you can just satisfy the demand using your beginning inventory, right? So you don't need to produce anything. That is a possibility. If you would like to produce something, well, at most you can only produce 1 because if you produce 2 and the demand is only 1 unit, then you will end up with 4 units in inventory, and that is not allowed, right? If you have 3 units at the beginning, you produce 2, it means now you have 5 units, but the demand is only 1 unit, then you end up with 4 units, and that is not allowable because our warehouse can only keep 3 units at most at the end of any period. So that's why you see here, if the beginning inventory equals 3, the only possible decisions are 0 and 1. Another example, if you do not have any beginning inventory, so you have 0 beginning inventory, then you must produce at least 2. You can't produce 0 because the demand is either 1 or 2. You can't produce just 1 unit because maybe the demand is 2. And remember, you must satisfy the demand. So at least you must produce 2 units. And at most, you produce 4 units because I believe that is the maximum production capacity in this problem. Okay, so that's how you decide what are the possible decisions with respect to each of the value of the beginning inventory. Now for each decision, you calculate the production cost, 3 plus 2x for x greater than 0. If x is 0, then cx is also 0. Okay. And the expected holding cost is from this part here. If you just multiply this and add them together, you will get this value, right? I mean, half times I plus half times x minus half plus half times I plus half times x minus half times 2, you will get I plus x minus 3 over 2. So that is just the simplified of this two term. And then for the salvage value, similarly, you just multiply the half times 2 plus what is inside the bracket, half times 2 minus whatever inside the bracket. And the total expected cost is the production cost plus the holding cost minus the expected salvage value. Because salvage value is something that we earn, so the sign is negative in this case, okay? Now here, if your beginning inventory equals 3, you have two possible decisions, and among them you pick the one with the minimum, with the smaller cost. So here it says that if at the beginning of month 3 you have 3 units in the inventory, the best decision is to produce 0 items such that your expected cost is minus 3 over 2. In other words, you earn 3 over $2. There will be a pause on this video to give you the time to calculate all the other F32, F31, and F30 just to make sure that you know for sure how to get all these numbers. Now let's move backward to stage T. So small t means that it is the month before the third. Same as before, we begin this month with the beginning inventory I, and then we are going to minimize the cost. The difference here is that before month 3, we do not have the salvage value. So we do have the production cost, same as before. We do have the inventory cost if the demand is 1, if the demand is 2. I'm sorry, there's a typo here. It should be I plus x minus 2, like this, okay? And same as before, you multiply each of this with the probability of the event happening. Probability of the demand equals 1. Probability of the demand equals 2. Now, because the ending inventory can be in this, can be in that, your beginning inventory at the stage T plus 1 can be this, can be that, which means that your FT plus 1 can be this, can be that. You just cannot sum them together because those FT plus 1, they're just different things. This one is the cost from the later stages if the beginning inventory is I plus x minus 1. That is the cost for the later stages if your beginning inventory is I plus x minus 2 in the next stage. They are different, so you must separate them. And then because it says if the demand equals 1, if the demand equals 2, same as before, you must multiply them with the probability of each event happening. Now, given the values same as before in stage 2, the possible beginning inventories are from 0, 1, 2, 3. And then same as before, if your beginning inventory is 3, your possible decisions is either producing nothing or producing 1 unit at most. You cannot produce 2 units because beginning inventory 3, if you produce 2 becomes you have 5 units, and then if the demand is only 1, then you end this month with 4 units, and that is not allowable because the warehouse can only keep 3 units at most, okay? So that's why you see for the beginning inventory 3, you only have 0 and 1 here. Same as before, calculate the expected holding cost, which is this, and then the expected future cost. You see that you cannot sum these two terms together. They are still separate. A half times the first ft plus 1 plus a half times the next ft plus 1. There will be a pause in the video to give you the time to do the calculation to make sure that you know how to get the values for each column, and then finally the conclusion in the last column. How do you get this conclusion? You need to make sure that you can do all of those things, okay? Finally, we have arrived at the beginning of the problem. If you read the problem carefully, it says that we have one item at the beginning of this problem. So I equals 1 for stage 1. Because I equals 1, at most we can produce 3 units, because one inventory at the beginning plus 3 that we produce, we have 4 units. If the demand only 1 unit, it means that we will end this period with 3 units, and that is okay. If the beginning inventory is 1, then we must produce at least 1 unit. We cannot produce nothing because if the demand is 2, then we don't have enough items to satisfy the demand. That's why the possible decisions, you see X here, is 1, 2, and 3. Same as before, this is the production cost, this is the expected holding cost, this is the expected future cost. And from all of these possible decisions, the minimum expected cost happens here, which means that we produce 3 units. So the minimum expected cost is 65 over $4, and our optimal decision in the first month is to produce 3 units. So from the previous slide, we have seen that, okay, the first month we must produce 3 units. However, because the demand at the first month is probabilistic, it means that we cannot know for sure what is the ending inventory of month 1. Or in other words, what is the beginning inventory of month 2. So that's why we cannot determine month 2 decision until the actual demand of month 1 is observed. If the month 1's demand equals 1, we will go to F23 because the beginning inventory of month 1 equals 1. We produce 3 items, so 1 plus 3. If the demand is 1, then we will begin the next period with 3 units. However, if the demand is 2, we will check out F22. See, it is different with the deterministic dynamic programming, which we can just, once we have solved stage 1, we can just trace this asterisk symbol, and then we know what we need to do in the second month, what we need to do in the third month. In this case, we just cannot do that because we cannot make the optimal decision until the actual demand of the current month is observed. Now suppose this happens. Now assuming that the demand of month 1 equals 2, we will start month 2 with the beginning inventory equals 2. Okay. From here you see that it would be best to produce nothing if this is the case. So the decision for month 2 is producing 0 unit. What we need to do to determine what we need to decide in month 3 is wait and observe until we obtain the actual demand that actually happens at month 2. If the demand equals 1, we will go to F31. If the demand equals 2, we will go to F30. Again, assuming that the actual demand of month 2 equals 2, we will start month 3 with inventory equals 0. Here we see that the best decision is to produce 2 units. The key in interpreting the optimal solution of the probabilistic dynamic programming like this is that you just cannot decide for the next period before the actual demand happened in this period. So you must wait until the demand at this month actually happened, such that you know your beginning inventory for the next month. By then, you can decide what you should do in the next month. So you just cannot know the optimal decision for all months since the beginning of the problem. So in this kind of problem, there's something called the SS policy, small s and big S policy. For example, let's take a look at the period 2. It shows that if our inventory is 2 or greater than 2, then the best decision is to produce nothing. However, if the beginning inventory is less than 2, the best decision is to either produce 3 minus I or 4 minus I. So if I equals 1, we will produce either 2 or 3. If the beginning inventory is 0, we will produce either 3 or 4. In this case, the small s is 2, is the boundary of inventory that we don't need to produce anything. And then the big S equals 3 or equals 4 in this case. It tells us the amount that we still need to produce, like 3 minus I, given that the beginning inventory is I. Okay, so that's the end of this video. In the next one, we are going to look at just the formulation. Here we are still doing the numbers and calculations. In the next videos, we are going just focusing on formulating the recursions. So see you on the next one. Thank you.